Hello students, welcome to today's session. We are on a mathematics topic, that is area approximation, and today we are focusing on estimating area using the trapezium method. In the other session, we looked at estimating area using the counting technique, where we get our irregular shape or our irregular graph on a grid, that is 1 centimeter square grid. We count the number of complete squares, we count the number of incomplete squares, and we saw how we use that technique to estimate the area. Remember, this is all about estimation. Most of the times when we go to the lab, either to do a biology practical, a chemistry practical, a physics practical, we do come up with data which we plot graphs, and at times we need to analyze those graphs, and when we analyze the graphs, we realize some quantities, we get them from the area under the graph. We could be having the equation of that graph, and at times we may not be having the equation of that graph, but that should not hinder us from at least getting the approximate area of that particular graph. So today we'll be looking at the trapezium method, and just to refresh our minds that we calculate the area of a trapezium. This is a trapezium which has two parallel sides. We denote them as side A and side B, and a certain height h. And the area of a trapezium is given by a half, the sum of the two parallel sides multiplied by the height. So this is a half A plus B, then we multiply that by the height. We'll be looking at the trapezium method by focusing on an example here, where we'll see how we can calculate the area using the trapezium method. Looking at the question we have here, estimate the area bounded by the curve. Estimate the area bounded by the curve y equals to x squared, the x-axis, the lines x equals to 1 and x equals to 5. That is, we need to estimate that area. It is bounded by 4 boundaries: y equals to x squared, the x-axis, the line x equals to 1, and x equals to 5. Definitely, we'll start by plotting the graph of y equals to x squared, and I've chosen a simple graph. If we are to get a table for the same, then we'll have when x is 0, then y is 0 squared, that gives us 0. When x is 1, this will be 1 squared, 1. Then when x is 2, y will be 4. When x is 3, y will be 9. When x is 4, y will be 16. And finally, when x is 5, y will be 25. I have a sketch of the same graph on the whiteboard here, and we want to see how now do we get the area using the trapezium method. The first thing we need to do is to note these boundaries. We already have the graph. This is y equals to x squared. That's our first boundary. Then the second boundary is the x-axis. That is the x-axis. Then the lines x equals to 1. That's the line x equals to 1. And the line x equals to 5. That's the line x equals to 5. So this is the area we are interested with. So the simple thing we do is divide this region into trapeziums. In the first case, we want to use 4 trapezia. We are going to divide this region into trapeziums where the height of the trapezium will be along the x-axis. The length along the x-axis is from 5 to 1. That is, the length here is 5 from 1 to 5, which will be 5 minus 1, which will give us 4. We want to use 4 trapezia. Therefore, what will be the length of each trapezia? That will be the number of trapezias is 4. The length is 4. So the height of each will be 4 divided by 4, which gives us 1. So after every 1 unit, we get a trapezium. So that is our first trapezium. This is our second trapezium. That is the third trapezium. And that is the fourth trapezium. Please note, by assuming this to be a trapezium, then we are assuming that this upper part here is a straight line. And when we take this to be a straight line, then it means that we have included a part here to be part of the graph, which is not really part of the graph. In the second again, we are assuming that this is a trapezium. If I draw a straight line here, it includes a smaller part there that is not part of the graph. Therefore, we are now going to take each of these as trapeziums. And you can see by so doing, they are including parts outside the graph to appear as if they are inside the graph. And that is why we are saying we are estimating. So we now go ahead and say the area of this region will be the area of this trapezium plus the area of this trapezium plus the area of these trapeziums. That is all the 4 trapeziums. The height here is the value of y. Note this is x is 1, y will be 1 squared. So the length of this is 1. The length of this at x equals to 2 will be 4. The length of this is 9. This is 16, and this is 25. These lengths here, we call them ordinates. How many ordinates do we have? 1, 2, 3, 4, 5 of them. For how many trapeziums? 1, 2, 3, 4. And therefore we go ahead and get the area. The area will be equal to the area of trapezium A, or 1, plus the area of trapezium 2, plus the area of trapezium 3, plus the area of trapezium 4. So the area of trapezium 1 will be a half. What is the length of A here? This is 1, and B is 4. Please note that all the trapeziums have a common height. The height here is 1. This is also 1, because it is 4 divided by 4, which will give us 1 unit. That means that the first will be 1 plus 4 multiplied by a height of 1. That is a half A plus B times H. So I have 1 plus 4 times 1, and this will give us 5 divided by 2, 2.5. The area of trapezium 2 will be a half. Let's see. The second trapezium here, this is 4, this is 9, so that will be 4 plus 9 times 1. This is 13 divided by 2 to give us 6.5. Then the third trapezium here will be the area of the third trapezium. A half into 9 plus 16 times 1. This is 25 divided by 2, 12.5. And finally, we'll have the area of the fourth, which is a half into, this is 16, this is 25. So 16 plus 25 times 1, which will give us, if I use my calculator, 16 plus 25, that gives us 41, which will be 20.5. And therefore the total area, the area of that region, will be 20. We add this and this and this and this, which will give us an area of, very fast here, 2.5, an area of 42 square units. And that way, we have been able to estimate the area of this region using 4 trapezia. What would happen if we were to use 2 trapeziums instead of 4? So with the same question, we still want to find this area, but now instead of using 4 trapezia, we use 2 of them. So how do we go about this? I'll still first go back to the length at the base. The length is 5 minus 1. I have a length of 4 units. Then I need 2 trapezia. Therefore, what will be the height? The height will be 4 over 2, which will give me 2 units. Therefore, from 1, then 2 units, the first trapezia will be from x equals to 1 up to x equals to 3. You notice by taking this trapezium here, we have taken a bigger trapezia than we had in the first case. And this makes now a bigger region that is outside the graph to be included in our calculation. Therefore, we are introducing a bigger error. If, again, the next will now be from 3 to 5, 2 units. Then again, that is the trapezium that we'll be having. It has included a bigger area that is outside the graph. Therefore, the area will be the area 1 plus area 2, because we'll be having only 2 trapeziums. And straight to the area of 1, it will be a half. The length here at 1 is 1 unit, plus at 3, that will be 9, times a height. The height here is 2 units, therefore times 2. That will give us 10 units. Then again, for the second one, from 3 to 5, area 2 will be a half. The length here is 9, plus the length here is 25. That is, we are multiplying by 2, and the 2 will cancel out to give us 1. 25 plus 9, that gives us 34. And therefore, the total area, when we use 2 trapeziums, will be 10 plus 34, which will be 44 square units. And you'll notice that this 44, later when we look at integration, we'll be looking how to get the exact area using integration. And you'll find that we've created a bigger error in 44 than we had in 42. And you can see the 2 trapeziums have included a bigger area outside the graph than when we had smaller trapeziums. Therefore, for the value of the estimation to be closer to the exact value, then we need to use trapeziums which are small. We need to take a small trapezium so that the curving, when you take a small trapezium, that curve will almost be a straight line. In the next session, we'll be looking at coming up with the trapezium rule, or what we call the trapezoidal method. Join me in the next session.